In this video, I'm going to be discussing both the power and absorption of electromagnetic waves. We're going to start with the power and then move on through to absorption. So the energy density of an electric field can be expressed as UE is equal to 1/2 epsilon naught E naught squared. And that has units of joules per meter cubed. E naught here is the peak value of the electric field. We're going to go ahead and do the same thing for the magnetic field and see that it can be expressed as UB is equal to 1 over 2 mu naught B naught squared. Again, with units of joules per meter cubed. So this is the energy density of the electric field, and this is the energy density of the magnetic field. But we also know that B is equal to E divided by C. So if we plug that in, we see that UB is equal to 1 over 2 mu naught E divided by C all squared. But now we know that C is equal to 1 over the square root of epsilon naught mu naught. And so if we plug that in, we will see that UB is equal to 1 over 2 mu naught E squared over 1 over epsilon naught mu naught, where we lost the radical because we squared it. Now these mu naughts cancel out. This epsilon naught gets brought up top, and you see that UB is equal to 1 over 2 epsilon naught E squared. And again, that has units of joules per meter cubed. So this is a very interesting result because it tells us that there's the same energy density in the magnetic field as there is in the electric field. So if we then wanted to calculate the energy density of the entire electromagnetic field, we would simply add these two together. So U total is equal to UE plus UB, or U total is equal to epsilon naught E squared joules per meter cubed. Now imagine we have a collection of electromagnetic waves traveling in a vacuum, and you'd like to know how much power is in the electromagnetic field. Well, given the energy density of the electromagnetic field that we just found to be U total is equal to epsilon naught E naught squared joules per meter cubed, we can imagine that this field is passing through a plane the size of 1 meter squared and perpendicular to the direction of wave propagation. In order to derive the power, we ask the question, how much energy passes through this plane in 1 second? Or simply, what is the energy flux of the electromagnetic field? Well, light traveling in a vacuum will travel a distance c in 1 second. That's 300,000 kilometers. This side of this box will represent that distance c. This side of the box is the 1 meter squared plane. So now I'm going to calculate how much energy comes through this 1 meter squared in 1 second. Well, the volume of this box is c meters cubed. and all the energy inside of this box will travel through this plane in 1 second, because all of this light will travel the distance c in 1 second to be on this side of the box. So in order to calculate how much energy flows through this plane in 1 second, we use the above energy density of epsilon naught E squared joules per meter cubed, and we multiply it by the volume of our box, which is c meters cubed. So an energy of epsilon naught E naught squared c joules is what flows through our box in 1 second. This is what passes through our plane in 1 second. So this can be written as joules per meter squared per second, or watts per meter squared. This is how much power is contained within our electric field. So the power flowing through any unit area of our electromagnetic field is epsilon naught times E naught squared times C, watts per meter squared. But we know that E is equal to B times C. So this can be expressed as epsilon naught E naught B C squared watts per meter squared. And again, we know that C is equal to 1 over the square root of epsilon naught mu naught. So this expression becomes epsilon naught E times B times 1 over epsilon naught mu naught. And again, the radical is lost because C is squared. So this can be simplified to E naught B naught over mu naught, or E naught H naught. And since power transfer is in the direction of propagation, and in a transverse electromagnetic wave, this is perpendicular to both the E and B fields, we can define a vector S that is equal to this magnitude and perpendicular to both the E field and the H field. And we express that by E cross H. This expresses the energy flux of the electromagnetic field. But since both E and H are sinusoidal functions, each oscillating in time with a frequency of omega, they are expressed as E is equal to E naught cosine K dot R minus omega t in a random n hat direction, Well, the H field is equal to 1 over eta naught k hat cross the E field, which can be simplified to E naught over eta naught cosine of k dot r minus omega t in the direction of k cross E. The vector S is also a function of time, because by multiplying both of these together, we are still a function of time. And in fact, that function oscillates with a frequency of 2 omega, where at any time t, the instantaneous power can be found by E cross H. But because these fields are oscillating, it is more meaningful to find the time-averaged energy flux. So given that the average value of cosine squared is 1/2, and we are multiplying these two cosines together, we find that the time-averaged energy flux vector can be expressed as 1/2 E0 H0 or E naught squared over 2 eta naught. And that is in the direction of propagation. We call this the time-averaged Poynting vector, while just S is called the Poynting vector. Once again, the time-averaged Poynting vector is far more indicative of the power contained within the electromagnetic field. I'm now going to switch gears and talk about the absorption of electromagnetic waves. So in conducting media, we can no longer assume that the current in the medium is zero, as we did for simple media. Incorporating a new current density term, represented by J, equal to the conductivity sigma times the electric field, three of Maxwell's equations stay the same: the divergence of the electric field, the divergence of the magnetic field, and the curl of the electric field. But the curl of the magnetic field gains an extra term, where it will be equal to mu epsilon times the time derivative of the electric field as before, but now plus mu times sigma times the electric field, where once again sigma times the electric field is equal to the current density. Now we want to obtain a wave equation for the electric field in conducting media. So multiplying equation 3 by -1 and taking the curl of both sides, we then apply a vector identity where the curl of the negative curl of a vector field is equal to the Laplacian of that vector field. So here we have the curl of the negative curl of the electric field, which we're going to replace by the Laplacian of the electric field. And that is equal to the time derivative of the curl of the magnetic field. We're going to call this equation 3a. Now, we're going to substitute Maxwell's fourth equation for the curl of the magnetic field into equation 3a for this expression, the curl of the magnetic field. So we get that the Laplacian of the electric field is equal to the time derivative of this entire expression, mu epsilon times the time derivative of the electric field plus mu sigma times the electric field. We're then going to take this derivative, so we find that the Laplacian of the electric field is equal to mu times epsilon times the second time derivative of the electric field plus mu times sigma times the first time derivative of the electric field. Now this is our new wave equation. You'll notice that this is actually the wave equation that we had for simple media, where this is now a new term that we call a damping term. And now we would like to obtain a solution to this equation. If we assume that the electric field E is space and time harmonic, it can be written as E complex is equal to E complex naught times an exponential. We then want to find its derivative, and this becomes very easy because it's an exponential. So the derivative is equal to negative I omega times the complex amplitude of the electric field times that exponential. Its second derivative can then be found as negative I omega times negative I omega times the complex amplitude times the exponential. We're going to multiply this out. And we're going to get I squared omega squared times the electric field. But we know that I squared is equal to negative 1, so this can be further simplified to negative omega squared times epsilon naught, times the complex amplitude times e minus I omega t. We can then rewrite our wave equation using our new electric field as well as its two derivatives. So doing this, we get that the Laplacian of the complex electric field is equal to negative omega squared mu epsilon times the complex electric field minus I omega mu sigma E times the exponential to make up the complex electric field, where once again, all we've done is substituted our proposed electric field, as well as its derivatives, into our wave equation for the electric field and its derivatives. Now, noting that this exponential exists in all terms, we can get rid of it, and our expression becomes the Laplacian of E. We're also going to bring both of these terms onto the left-hand side of the equation, so it'll be plus omega squared mu epsilon times the complex amplitude of the electric field plus I omega mu sigma times the complex amplitude of the electric field is equal to 0. And now we're just going to factor this expression to get that the Laplacian of E plus omega squared times the complex amplitude of the electric field multiplied by mu times epsilon times 1 plus I sigma over omega epsilon is equal to 0. And we're going to call this equation 6. Now, if we assume a monochromatic plane wave, we can suggest that a solution to equation 6 is of the form a complex amplitude multiplied by an exponential with this wave vector k. But the wave vector k is now a complex quantity of the form k equals k plus I kappa. So the wave vector k is equal to a real k plus I kappa. If we do that, and we plug that in to our proposed solution, then the electric field is equal to a complex amplitude multiplied by this exponential, where now the wave vector k is a complex quantity, all multiplied by z minus omega t. And we can simplify this by first distributing the I and the Z. We can then use exponent rules to separate this and obtain e to the I squared kappa z multiplied by e to the I kz minus omega t, all in brackets. There should have been an I there. But I squared, we know is -1. So this becomes e to the negative kappa z times e to the I kz minus omega t, where this is of the same form as our solution in simple media, except we have this extra exponential, which represents decay. So as our wave propagates through the conducting medium, it will decay. And we can find the values for k and kappa in our complex wave vector as follows. K is equal to omega over c. We're going to open a big radical. Epsilon r mu r over 2 multiplied by another radical with 1 plus sigma over omega epsilon r epsilon naught squared, all of that under the radical, plus 1, and then we close the first radical. And kappa looks very similar. Open up that first radical. Epsilon r mu r over 2 multiplied by a second radical, 1 plus sigma over omega epsilon r epsilon naught squared. But now it's -1 for kappa. And then we close our first radical. So these two quantities represent your k and kappa respectively for your complex wave vector that is then present in this electric field.